Hi all, here we go again, and we're going to be talking about inverse trig functions. And when you think about the graph of sine of x, it should be pretty clear that its inverse is not a function, because the graph of sine x does not pass the horizontal line test. So let's just take a quick look at some of these graphs. So here's the graph of y equals sine of x, and there's so many places where we could draw a horizontal line, anywhere between y equals 1 and minus 1, that will hit that more than once. And you should remember from algebra 2 that if a function fails the horizontal line test, then its inverse is not a function. So let's just take a look at what the inverse of this function looks like. So here is the inverse of sine of x, where we flip the x and the y axes. And we want to learn how to write this. And so we write this as y equals arc sine of x. That's a special notation that we use for the inverse of a trig function. Some books, many books, unfortunately, will write it like this. And I frankly don't like that notation. It's confusing. It might make you think that that means 1 over sine of x. So this notation is much easier to understand. It's simply the inverse of the sine function. And as we said before, it fails the vertical line test, and so this is clearly not a function. So the big question then is, what can I do with sine of x to ensure that its inverse will be a function? So there's the big question. What do I do? How do I kind of cut down sine of x so that it passes the horizontal line test and so that its inverse is a function? Whoop. Yes, that shouldn't be apostrophe s. So here's how we do it, and there's a lot of ways of doing it, but what we do is we just restrict the domain to minus pi over 2 to pi over 2. So let's take a look at that particular graph. Okay, so this is the graph of sine of x, but it's restricted to the domain minus pi over 2 to pi over 2. And this function, although it's part of sine x, has its own name, and we call it principal sine of x, and we indicate that with a capital S. And now, if you notice, anywhere I draw a horizontal line, I'm only going to hit once. So the inverse of this is a function, and it does attain all values from minus 1 all the way up to 1, and so it reaches all the possible values that sine reaches. So this particular function, y equals principal sine of x, has an inverse, and the inverse will be as follows. So, what have we got? The inverse of this function is this function. And this is the inverse of principal sine, and we name it with a capital A to indicate that it's the inverse of the function principal sine. Now notice what its domain is. Its domain goes from minus 1 to 1, and its range goes from minus pi over 2 to pi over 2. And this is the inverse of principal sine, and we call it arc sine. So it becomes very important now to come up with a formal definition of arc sine. And if you're able to remember this definition, then you will do well. So remember how the graph of arc sine of x looks. So the domain is minus 1 to 1, because we can only talk about angles whose sine is somewhere between minus 1 and 1. but more importantly, the range is minus pi over 2 to pi over 2. So here is the formal definition of arc sine of x. So let's look at some examples. Suppose we're asked for the arc sine of 1/2. Well, there are lots of angles whose sine value is 1/2, but there's only one angle whose sine is 1/2, and that with that angle being between minus pi over 2 and pi over 2, and that angle is, take a second, think about the unit circle, what is it? Very good, it's pi over 6. And how about if we ask for the arc sine of minus 1? And again, there's lots of angles where the sine is minus 1, but the only one between minus pi over 2 and pi over 2 is minus pi over 2. So this is why I mentioned earlier how important it is to master the unit circle, because if you have a good picture of the unit circle, then you can answer any of these questions. So here it is again, the unit circle. And just to show you how you want to read this, here we are at what we sometimes call 3 pi over 2, but it's better right now to call it minus pi over 2. And then we go up to pi over 2. And the y values, remember the y values are the sine values, are going from minus 1 to 0 up to 1. And so when I ask the question, say, what is the arc sine of 1/2? I'm saying, okay, where is the y value equal to 1/2 between minus pi over 2 and pi over 2? It happens right there at pi over 6. Where is the y value minus 1 between minus pi over 2 and pi over 2? It happens right there at the bottom at minus pi over 2. So that's why it is just so important to have this unit circle memorized and understood. So now let's talk about cosine. And what I'll do is I'll put up the 4 corresponding graphs for cosine and just kind of talk about the same things that we did for sine in much less detail. Alrighty, so here's a lot to look at. But these are all the important graphs. So this is the graph of plain old cosine. Periodic, going from minus 1 to 1. Here's the inverse of the cosine graph, which itself clearly is not a function. Here is the restriction that we make on cosine, and we call this principal cosine. And the restriction is 0 to pi. So we're going from 0 on out to pi, and as we do that, cosine achieves all possible values from 1 to minus 1. And the inverse of principal cosine is arc cosine with a capital A, and it looks like this. The domain is minus 1 to 1, the range is 0 to pi. And that is the way that these graphs for cosine are developed. We won't look at the remaining 4, but once you have understood what goes on with sine and cosine, you should have no trouble constructing the inverses for the remaining 4 functions. Maybe just in passing we'll take a quick look at tangent, because the way it behaves is kind of cool. So let's put up the graph of what y equals tan of x looks like. So here's the graph of y equals tan of x, and in order to make it, and obviously its inverse is not a function because tan x fails the horizontal line test. And so the restriction that we put on tan of x, so its inverse is a function, is we look at this much of it, and we call that principal tan. And so the restriction then is from minus pi over 2 to pi over 2, not including the endpoints because tan is not defined there. And so what does arc tan of x look like? Why don't you play with it for a second and then press pause, and then I'll put the answer up. So if we go back and just look at tan, I just filled a little bit of this in. Here's the domain of principal tan, and here's the range of principal tan, all reals. So the domain and range switch when we look at the inverse function. So here's the inverse of tan called arctan. And what's particularly interesting is that we actually have horizontal asymptotes here and here. Here at minus pi over 2 and here at pi over 2. So when you get to calculus and you start looking at limits a lot more, one of the ways that we can express this relationship is by saying that the limit as x approaches infinity of arctan of x is equal to, well, think about it, as x is getting bigger and bigger and bigger and bigger, arctan of x is approaching, have you got it? Just pi over 2. Kind of interesting. So that'll conclude it, and I'll leave you to think about arcsec and arccosec and arctan. But now you know the basics of the inverse trig functions. Congratulations.